we will look for anything is missed in the previous two meetings. And I think we did miss so who is doing last subject? Okay, so last subject of practical applications. Then Joshua is doing commutation, right? Okay, and let's check what else we are missing. So visualization, I think it was partially covered last time, but maybe we need to look again. Okay, I'll probably cover things that were absolutely missed last time. So we'll focus on the commutations and examples. And let's look. Did we cover, well, maybe White is a main person for this thing. White, to your memory, is anything we are missing for properties of operators?
I don't think so.
Okay. Yeah, feel free to stop me, especially at the end of the meeting, so to additional comments, but we'll consider this is already done. So commutation will be our primary focus. Conversion between momentum and position, it was partially done. I'll maybe mention quantum dynamics was done, initial conditions was done. Alternative methods, I think it was done, but my memory may not serve me well, so feel free to stop me and request anything. Well, since Adam is coming less frequently than you, maybe you'll just focus on the subject and back up to minimalistic level. Just look for something from previous years and maybe make shorter presentation. But if Adam misses our presentations, the class will still have this subject. So it's very basic, and I'll assist if needed. Accumulation expectation values. So saving computation expectation values. I think it is what we were talking last time. So do you feel comfortable and safe?
Yeah.
Okay. Real and imaginary parts of the wave packet. For my, we basically done it. I also do not have full guarantee of if my will come and present adequately, but it seems quite simple things. So this was done last time. Visualize potential and probability distribution. Well, I think this part I may want to cover today. And groups of observables, maybe I'll briefly chat about it, but we did it in the past. So I will, if time allows, I will try to do an example of movies, but I think we did enough of it in the previous time, and you all have an idea how to generate movie and upload it to YouTube, right? And yep, and then I'll cover this time. So reasonable if I focus more on this whiteboard. So if we go into the internet and look for commutation between position and momentum, I just don't want to waste your and mine time in going over derivation or writing. Have you? Does this equation looks new for you, or you feel comfortable with it? Please confirm if it is, if you're absolutely comfortable, absolutely non-comfortable, or you have heard something in class. Oh, okay. At least Joshua is comfortable because it will be your presentation. So, well, do you feel comfortable with this equation, or is something you're not sure? Do not hesitate. You can just show it in a hidden form.
I mean, I know what they all stand for. What's it trying to describe?
So in the classical approach and in our regular common sense, if you multiply two things, two numbers or two functions, it doesn't matter in which order, right? In here, it is so this means xp minus px, right? So you swap by common sense, this should be 0, right? But it is not, because those are quantum operators. And one should understand that everything we are writing here has a function of x. So it means x ddx times phi of x minus d dx times x times phi of x and some constants up front. Make sense? And these operations of differentiation and multiplying by function are not equivalent. If one performs it, one is getting that it will be original function multiplied by this constant. Better? And this red writing was done in the format of differential operators, but if you do it in format of matrices, it should hold as well. So this is one of the fundamental properties of in quantum theory. And if our modeling is done correctly, it is expected to hold. So when we do our MATLAB modeling, we should check that this property is matched. So if it is matched, our theory is 100% correct. If it is partially matched or not matched, we should be careful. Make sense? So please open your MATLAB equipment and run the same code as we were doing last time and last Wednesday and previous Wednesday. So I would like to check if you have already if you did run the code and you have the all variables after running the code active.
Let's just go.
Okay. So it should be window with images.
Images.
Yeah, can you bring it up?
Uh,
No, it's already there. You just need to learn how to operate it. Maybe click on view
okay.
and check. Maybe expand all.
Expand.
Uh-huh.
Expand how?
Yeah.
Okay.
So, or maybe clicking here, there will be several. So can I touch this?
Alright.
So there should be no. So we need to bring up the command window. If you
And with the
okay, maybe let's try to do it once again. Okay. So just play with it and I'll show it to everyone as well. What it is. Okay, very good. Yeah, it's still running. I think it's going on. Did everyone online got this code running? So if you didn't, let me know. If you did, then I'll assume everyone has already completed it. So let's look on. Let's do the following command. So if I, well, maybe just copy paste this command and try it, and I will try to give additional explanations. It could be the quickest way. So I'm looking for momentum operator and position operator, and then I'm combining them in the same way you see here, as we found online in the definition of canonical commutation. So position operator, momentum operator, position operator. And if I look once again into this commutation, you see, so position first, momentum second, and then it is expected to be equal to identity operator, Planck constant, and imaginary unit. So if I want to do images, like three-dimensional images, I cannot plot numbers, functions that have both real and imaginary parts. I need to specify what I want to plot, real or imaginary. And since I suspect that it will be imaginary, I put here IMAG, and then in brackets this stuff. Then after the brackets, I'm using this axis command, because if I do not do it, the main feature will be not very visible. So what do they mean, and where did I got these numbers? So if I type size it tells 100 by 100 or 200 by 100. Both of these operators have size 200 by 200, and this is x-axis beginning to the end, y-axis beginning to the end, z-axis beginning to the end, right? So I just narrow down the range of exploration. And here, when I'm doing it, I'm getting the figure which shows a feature along main diagonal, which has height of 0.5, and it is zeros in other vicinity. If I do not do this axis operation, then it shows some values at the very far off diagonal with high values, which makes our main feature mostly invisible. And whoever presents it may want to make a comment or discuss what's the reason for this feature. And the answer is that one needs, so what we use is not actual truly true momentum operator, but momentum operator which already takes into account boundary conditions. The fact that wave packet can exit the door and enter the wall. It makes sense for you? Well, does it make sense? Okay. If here I put real instead of imaginary, it shows 0 everywhere. So this result of commutation in real domain is 0. So we have partial coincidence with the expected result. So it is imaginary. We set Planck constant equal to 1. Here we get 1/2, but we get at least the fact that commutation is not 0. It's similar to identity operator. It is imaginary, but with some adjustments. So where in the code this momentum operator by a third method is defined? So it is line 124, and there is another method that we originally discussed. So it's the third method, index 3 in this px3 means that it is third method. And if we look here, there is a definition of momentum operator through Fourier transform. We may want to check if it works better or worse, and I expect it will work worse. So it shows some very different results. So it has some features along main diagonal, but the features on the far from main diagonal are substantially bigger. And, if I look on the real part, it's 0 on main diagonal, but far from 0 away from the main diagonal. So from this analysis, one can say that results made by method 2 are less reliable. So if you need to do something for like publication or with guarantee of success, method number 3 would be better. But we still keep method number 2 because it's a little easier to explain what it is. So it is more logical. So I would like to make a quick tour over everyone who is in class and then everyone online, and make sure you can show this figure. So it will, and you feel comfortable like generating this figure and then rotating the image and bringing it to the shape. So first in class, second online.
I did have.
Okay, excellent. Yeah, thank you.
And the other one. And was this.
So do you have an idea how to explain it?
Not that I could remember.
But please think and try to right now you can copy paste images into PowerPoint and start doing your presentation right now.
All right.
Okay. Okay, yeah. Thank you, John. Okay. 0 to 100, 0 to 100, space -1. Not no. -1, space 1. Close this, enter. Let's see what happens. Okay, excellent, thank you. So let me invite Alison, would you like to share screen? Oh, I probably should stop sharing first. Alison? Okay, excellent. Thank you. You can stop sharing. It's enough. Yes. Make host. Yes. Sibel, would you like to share screen? Yeah. Okay. Excellent. Yeah. Thank you. You can stop sharing. Who's next? Adam, would you like to share screen?
I got here a bit late, so I don't have the code written.
Okay, but still, let's we'll all wait. It's better if we constructively solve all problems right now. So if you, I made you a co-host, and if you share screen, we'll figure out all things. It will be much quicker. So yeah, I see you have some codes. You need to find a code. I think I sent it like 2 weeks ago. It's the name starts with WP for wave packet, and then long name .m.
Okay.
I can resend, or you can just browse through your email.
I can look through my email. But
Huh? Well, let's do it. Let's open it right now. If you, it will be really quick.
okay. I can't find. Oh, I found it. Yeah, here it is. Is it which file is it? WP underscore
Exactly.
HO.
Yeah, you found it much quicker than I did.
Which one is it? There are three that have WP in them.
If you stop sharing and then start sharing the whole display rather than only MATLAB window,
Oh yes, sorry.
I will be able to see what you're doing.
Okay, let's see. Okay. Yes. Okay. Here's.
So can you click so that we see all? Well, download all of them, but not the last one. It's either first.
Oh. Okay.
And for this exercise, it doesn't matter which one. We can. They are very similar. They differ only by one line. Okay, now you see play green triangle. Yeah. So run. So you see at the left lower corner, it types busy. Now it tells pause, press any key. Please follow by pressing. Now you see some movies developing. Busy in the lower left. Busy, 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 busy. It's more than half. It's almost done. Now it will garbage your screen with different images, and now it is ready. So you can close windows so they do not garbage our view. Just close all of them, not all, but all figures. Yes, this and this and this. And now type in the command window. Yeah, here the same thing I shared with everyone in the chat.
Oh, it's
Or
in
I
the chat.
can dictate it. Mesh, MESH, open bracket, IMAG, for imaginary, yeah, open bracket, not close, but
Oh, open. I'm sorry. Yeah.
uppercase X, lowercase OP for X operator, star, uppercase P, lowercase x, number 3, minus the same symbol px3, uppercase P, lowercase x, px3, star, uppercase x, lowercase op. Close, close. Enter. So, and then select, yeah, by rotating, put it to watch the main diagonal. You see, it's not very visible. Now go back to the command window, upper arrow up to save on typing. No, not.
Oh.
Semicolon, axis, AX. No. X, first letter A, second lowercase x, lower, all lowercase.
Oh.
X, E, S. Axis, open round bracket, open rectangular bracket, 0 space 200, 0 space 200, space -1 space 1. Close rectangular, close round, enter. So anyone in the class or online, why the,
X is with an I.
okay, let's arrow up,
Oh,
arrow up. And now, okay, yeah, thank you, Nate. Appreciate it. Enter. And now bring up the window. It's, yeah, click here.
ah,
Okay. So you are on the same page with everyone.
okay, yeah,
You can stop sharing.
thank you.
Okay. Wyatt, would you like to share screen quickly? Yeah, that's great. Thank you. You can stop sharing. Okay, so what is our next item? Conversion of operators between momentum and position. I think we did it during our first meeting, and maybe I'll. Joshua, do you remember it, or you're completely blanking on it? So right now we have. I'm asking on this question: conversion of operators between momentum and position. Do you remember what we did in the first meeting, or you're completely blanking? And
Yeah, it's
okay, I briefly remind, but please watch recordings of 2 weeks ago. Okay, so so this W operator is a key for transformation between momentum representation and position representation. If we take these lines from 99 to 103 together, then W operator will include the imaginary exponential with imaginary power, which will be which will have different values of position steps and momentum steps in the power. So it will be a square matrix, and multiplication of this matrix is equivalent to converting operator from momentum representation to position representation, or inverse. So let's type here same mesh P operator. So if you do, so P operator, I will show later what it is defined, but it is momentum operator in momentum space, which, so look here. And maybe I need to redraw it without this axis. So it shows, first of all, it is real. Second, it is matrix with zeros everywhere except main diagonal. And on the main diagonal, it scans different values from negative to positive, right? As an analogy, if I show X operator, which will be X operator in position space, it will be very, very similar. So a matrix which has zeros everywhere except main diagonal, and on the main diagonal it escalates. So it deals with linear algebra theorems that after finding eigenvectors of a matrix and making linear transformation in the space of this eigenvector, the original matrix becomes diagonal. So we can consider everything in position space as we typically do but we can move to momentum space, which we did at the very beginning of the class when we did Fourier transform and particle in the free space. Now, if we take back this POP, right? And now we are applying the procedure of converting momentum operator into position space. So if I do mesh px, I need to specify whether I want real or imaginary. So if I do real, it will be something small. If I do imaginary, it will be subtraction. So it will be positive and negative values in the vicinity of main diagonal. But it is a more precise way to define differential operator of derivative in finite differences. But here we are obtaining it through a Fourier transform. If I want to plot this W, it will be ugly. We do not want to. It's not healthy for humans to look on it. Same as if you were watching the new TV series Foundation. You didn't? So it has an episode when the character is flying between different stars in the like unrealistic speed, and they are put into hibernation. And then the character wakes up in the middle of this transformation, and robots appear in front of her and telling it's not healthy for humans to watch what is coming through Illuminator. So this stuff is only an operation, but if you want to add explanations, this is transformation from of wave function from position to momentum space, right? And if you do this operation twice, and backwards, phi of x will be integral phi p e plus I p h x, and now dp. And if you do this operation twice, e plus I p x h bar d p p in of p and p prime, and here we do e minus I h bar p prime x prime, and we do two integrals dp and dp prime. So it will be a conversion of the operator from momentum space to position operator in the position space. And in MATLAB, it is px equals w pop times w. Make sense? The resolution on recordings can be of low quality. If you need equations, you can just make it with your photo camera or reproduce it yourself. So are we done with this conversion of operators? Joshua, it's mostly a question for you. You will be presenting it. Okay. What's next? So we have 1 hour, 15 minutes. Our main goal now will be these applications, but they are pleasant and quick. let's make stops on the things we may want to be more comfortable. So discrete representation of wave function in space and time, normalization of wave function in discrete representation, size of the simulation cell versus time of simulation. Please raise hands who is absolutely confident in this subject, in these three subjects in the highlighted by blue. Nate? Oh, wait, who is halfway confident? Just by talking to you last week, so yes, no, completely no. Joshua? Okay, then I probably need to cover it. Let me quickly ask those online. So where's chat line? So Wyatt, Sibel, Ellison, and Adam, please make sign if you are absolutely confident with this question of wave packet passing through, or make it positive if you're absolutely confident, and say nothing if you need more comments. Okay, it looks like we need some comments. So when we jump to the very beginning of the code, we see this number of points. So number of grid space, grid points along position discretization, not space, I would say momentum. And then we are setting the number of points, size of the box, and increment of position. And somewhere here, yes. So we do set up the area of definition, the box, one-dimensional box, as a lean space going from 1 to a number of points, 200 points, and then each point is multiplied by dx. So basically, it is how did I formulate it? Discrete representation of a function in space. Now, when oh, does it make sense? Should be quite basic, right? So just several points to represent x-axis. Adam, does it make sense to you?
Oh yeah, that makes sense to me.
Yep, thank you. Now I'm jumping back to the beginning of the code once again. So n tau equals 700 something. So number of time steps. Tau is amount of time step. And when I'm going to the main loop, so which will start at the line, I'll tell when I arrive to the correct line. Okay, when I arrive to the beginning of the main loop, where we have propagation of the wave function, it goes over as many time steps as we defined at the beginning. And at each time step, we are making this propagation of a function by one time steps. So if you look back into definition of this g tau, which is evolution operator for method 2, G tau. Yep. So it includes infinitesimal time step. So each time we propagate forward in time, we move forward by the tau duration. And we do as many of those little steps as it is defined at the beginning. So we, oh, does it make sense? Okay, Adam, does it make sense?
Yeah.
Feel free to stop me. It's better if you achieve a full agreement on basics rather than I go to something where we lose each other. Okay, so this was discrete representation of wave functions in space and time. So we did discrete space and time, and now we need wave functions. So and it deals closely with initial wave function. So I'm browsing until I find the equation for psi naught. So we are intentionally setting up wave function at initial time as a product of Gaussian wave function. You should recognize this exponential of x squared centered at the x naught, which is defined at the beginning, times the plane wave, which is, so here is the second power of the position, and here is the first power of position, x times momentum. And then it gives plane wave, and it defines non-zero velocity. So at the same time, we have localization near the central point x naught and momentum p naught to define the velocity. And since this equation uses x, which is a like vector with 200 values, which are escalating, as soon as we plug in x into this equation, we will have psi naught as a vector of 200 values. Make sense? So it is what we were plotting when we have been here last time. So I will do some repetition. So I'll type plot with lowercase plot. Imaginary psi naught. If I put x, it will give actual values of value, and I can also do x, comma. Let's do here this way. So wave function is represented by specific points. If you connect them, it's only our perception, but it is a set of discrete points, right? So we represent mathematical function with a set of points. And this function, because it is complex, we have real and imaginary part. Real. So last time we were doing spiral, three-dimensional spiral, right? But some people get dizzy looking on three-dimensional object. This one is a little simpler. So real and imaginary are very close by amplitude, but they are offset by a half period, right? And these structures are centered near initial position, and they have momentum which shows density of fringes. Therefore, after we start the code, it starts moving forward. If we change initial value of momentum to negative, then this offset between green and orange will revert. So like they will swap the order, and then the wave packet will move in the other direction. But these two lines are initial wave function represented in the discrete basis. So I would like to ask to walk and make sure that you can plot this image, and those who are presenting can explain it. So first in class, second online. Huh? Oh, let me open the stuff. Yeah. It's not my intention to check your memory and guess the commands by memory. We need just understanding rather than memorization.
Yeah.
Yeah. I see it. You can just put X, skip these colors, X, comma, and then do real. Maybe there is another one. Imaginary and real. Let's arrow up and just try arrow up just to repeat the command, enter. We type figure, type the word figure, figure, enter. And now go back to command window and arrow up twice, enter. Oh, I know what is happening. You did set the initial momentum equal to 0, therefore you do not have fringes. I recognize this guess. So if you set P naught equals like, or just 1, and then save, rerun, and repeat the previous exercise. Okay. But first you need to run the whole code. You can arrow up to bring up this command. And now here it will show press any key. Busy, and after it is only after it is done, then rerun this command. Did you get it? Excellent, thank you. So it has less fringes because your initial momentum is probably like 0.25, right? So if you increase initial momentum, it will have more denser fringes. Okay. We have glorious accomplishment of this exercise in class, and let's look online. Wyatt, would you like to share screen? Okay, perfect. You can stop sharing. Sibel, would you like to share screen? Sibel, would you be?
Yeah, sorry, a minute. I was trying to.
That's okay. That's okay.
Okay, so.
So you're sharing on the. Yeah. Let's. Do you have the?
Hold on. Oops. So when I plot my C naught, it gives me this.
Okay.
So I don't know.
So let me request remote control.
Approve. Yes.
Okay. And I'm going to change P naught, make it a little bigger. Can you save and rerun the code?
Yes.
Save and run and bring up the window where it is running.
Okay. Oh. Oops. Okay. So, wait, hold on. Sorry.
So that's okay. That's okay.
Yeah.
No. This will not work. Let's do it this way.
Okay.
So PWD. So okay, and we have WP. Okay, wave packet. Now we hit enter to start it running. Now it's in the lower left. It asks press any key. It starts moving, and see it moves quicker, right?
Yeah.
Okay, moves quicker, moves quicker. Attention to Adam and Lola. You saw how the wave packet did pass through the edge. Okay, now we are closing these images with just to clear space. And now in the command window, typing this plot imaginary psi naught and then real psi naught. Make sense?
Yes.
So I do not know why both real and imaginary were 0. I was expecting that if the initial momentum P naught is 0, then imaginary part will be 0 and
0.
real part will be false. Okay, I think everything is great on your side. Any
Thank
questions?
you.
Okay, then you can stop sharing.
Okay.
Okay, let's see if Ellison maybe, okay, disconnected. Adam, would you like to share screen? And please bring up yeah. Perfect. Yeah, excellent. You can stop sharing. Now it's my turn to share screen. Okay. So let's look what is next. So we are absolutely done with this discrete representation in space and time. Normalization of wave function in discrete representation. Does anyone remember us discussing it together last week? Completely remembering, halfway remembering, not remembering at all? Do not hesitate. It's not for grade, it's for my, okay. I know we are wasting time, but better we will be confident on basics. So a goal of any theory and computation is to predict outcome of the experiment, reproduce and interpret. And this idea is hidden in the concept of observables and expectation values, right? Yes? Okay, which means we are, Joshua, I'm going to erase. Okay, so the concept of measuring something, finding observables is related to our sandwich operator. Psi xt star operator, psi xt without star dx integral will give expectation value of operator A at time t. So you remember it. So if our wave function is not normalized, if we multiply wave function by arbitrary number, then the result of measurement will be corrupt, will be wrong, right? So in order to have this value, we always need to make sure that if we remove A, that this psi star psi dx will be 1, right? And in order to make sure it is done, and also in order to make sure we include this dx, so if we just add together all discrete values without dx, it will be wrong answer, right? So if we replace wave function and operator by matrices and vectors and skip this dx, then we will get very wrong answer and we will be unable to predict outcomes of an experiment. Therefore, to have this issue fixed, we do have a specific but important thing here. So SQRT-dx. So since we are doing everything in discrete space, we do just psi 2 star times an operator, and we were discussing it last time. Under operator, it can be momentum, position, total energy, whatever is needed, dispersion, times psi 2. So row matrix column, row by column, and then row by column rule to get a number. In this construction, we do not have integration and we do not have dx, but we want to have it. We could either add multiplied by dx anytime we find expectation value, or we can just multiply the things, but then in the definition of the wave function at initial time, we do this everything which is needed times square root of dx. And then when we multiply wave function by operator, but wave function once again, this square root of dx becomes dx and pops up everywhere. Make sense? Ola? Adam, does it make sense to you? Or you do not?
Yeah, I think so.
Do you see what is written on the board, or it is completely invisible?
I can see it. Yeah.
Oh, okay, thank you. Let's check if we have normalization explicitly. So I'm going inside the loop. Okay, so even before the loop, you see this energy computed by method 3 is, sorry, energy computed by method 3 is wave function by method 3, Hamiltonian by method 3, wave function without apostrophe. But to make sure that it is normalized, one can divide it by the normalization factor, just recompute it again. So it's if the wave function was already normalized and is good, this will be 1 anyway, and we will not damage outcome. But if something happened or numerical error did accumulate, or even we did some human error with programming, at least we will fix error with normalization by dividing everything by this factor. Oh, does it make sense? Adam, does it make sense?
Yeah, makes sense.
Good. And if you scroll through, if you continue scrolling through to inside the loop, so first few lines after the loop, it is propagation forward in time, finding probability, and then later on, after there is a block of variables for observables. And there are some tricks to do special cases, but here, okay. So if you need to find expectation value of momentum, we do it by this rule, wave function conjugated apostrophe times operator times wave function non-conjugated. And we divide it by normalization factor, which is computed just a line before. And then this an additional measure to make sure that our results are trustable. And if we scroll further, you will see this trick done again and again for all operators. Okay, so we are done normalization. And now, last thing, size of the simulation cell versus time of simulation. Who remembers this thing from last meeting completely? Do not remembers at all or partially? Yeah, thank you, Nate. Okay. Let me do it once again. I see that you remember, but so original values at the beginning of the code were set up with quite small value of momentum, maybe 0.25. But if I set up larger value, right, it could be, so we need to balance, or we need to just think ahead. Right now, I'm looking only on a free space, just to have a simple situation, and we know how free space should behave from our in-class problem solving. So wave packet is going to move linearly, center of wave packet is going to move linearly. But what if during our simulation, wave packet will approach too close to the end of the box? What if we simulated so long, or initial momentum is so big that by linear motion it will go through the wall? What will happen after? Adam, can you try your freestyle answer right now?
Can you repeat the question?
I hope I can.
Or maybe, sorry.
Mental retardation, I can repeat my own words. Suppose we put too high of a momentum, or we perform simulation for too long time, and linear motion brings our wave packet away from the box. So it's like a you play rocket ball instead of tennis, or you play tennis and you miss the net around your court, and the ball flies away from your designated space. Do you it's not a question. Do you see the situation and analogy?
I'm not sure. I think so, maybe.
So if you are not in the closed room, but you are playing some sport game with a ball, and you just the ball goes away from the designated square, designated place of for the play, it can fly away, and then you need to go and pick it up, right?
Yeah.
Okay. So here we have area of definition localized by these 200 points. What if our wave packet approaches the wall? Do you expect it will bounce back from the wall, or annihilate and completely disappear, or something else? Like, what, based on your intuition, what is going to happen when the wave packet will approach the edge of the simulation cell?
It would probably bounce back, right?
Any other options? What else can happen? Oh, can you share your
I don't think it's going to come back from the other side. I don't know.
Okay,
what else.
yes, excellent. It is the answer I was expecting. Adam, did you hear Lola?
Yeah.
Can you repeat?
It will come back. It will come back from the other side. It'll just
How
appear in the.
do you agree, or can you interpret it? Does it look crazy?
No, that seems correct from what I saw when we ran the program.
Okay, so let me. I'm confident you all can run it, but I just like running code again and again. So if I set this high value of momentum, save and run. So we set up too high of a velocity. It approaches the edge, right? And then it reappears from the other side. So it may come through the wall more than once. If we do not want this effect, we probably should either use smaller, shorter simulation time or put a smaller initial value of momentum. So how do we interpret the image on the lower panel? Let me figure mesh probe mesh. Close. Okay, so Adam, would you interpret this image that I'm bringing up?
What do I interpret in it?
So, or maybe you, please, I will ask you to interpret it in 2 minutes. And right now, I'm asking everyone to reproduce this image.
Oh, okay.
Okay. Okay, great. Yeah, excellent, thank you. So where it is? That's fine, I'll explain to everyone. Yeah, you can erase figures if you are not going to save them. Maybe the last one. Yes. And if you select, put marker here, and yeah, you can rotate it. So it starts, goes there, and then reappears here. Make sense? Okay. So let me ask those who are online to share screen. Wyatt? Okay, perfect. Thank you. You can stop sharing. Sibel, please share screen. Okay, yeah. That's, oh, you can rotate. Yeah, please rotate. It's just pleasant to No, the symbol of rotation, then click, drag in the center and try to click and do not release, and then move your mouse. No? Okay, that's fine.
It's not rotating.
Maybe if mouse doesn't obey you, you can there is a
Yeah, it's not.
later on I'll share a command to rotate it in the command line, but anyway, it's a good image. You can stop sharing.
Okay.
You'll fix it later. Adam, would you feel comfortable sharing screen? Or would you be able to rotate this image? Okay, so please explain what are you showing, how to interpret what is shown. And I think your microphone is muted, or you decided not to tell
Oh, sorry. It just looks like the range of position values increases over time, just saying that uncertainty in position increases with time.
Nothing wrong, but how would you define this colorful yellow stripe? What it is?
Oh.
Like
it's like a distribution.
Distribution. Please repeat.
Yeah, like a distribution of I guess values, or I'm not sure. Probability distribution.
Probability distribution.
Mm-hmm.
As function of position and time, right?
Mm-hmm.
So it's probability to find electron or a particle at certain place at certain time.
Mm-hmm.
And
Yeah.
it moves with linear speed from left to the right, correct?
I think so.
So how to interpret that it reaches the far right edge and then reappears from far left edge? Can you point this points on the image and maybe add a comment?
So said add a comment, as in like write something, or?
Just
Oh.
add a verbal comment. Just speak something.
Oh.
Is it surprising? Is it amazing? Is it boring?
It's kind of surprising that the position just seems to reset towards zero.
Okay. So if we take this image and copy paste it in the PowerPoint several times, maybe let's do it while you are sharing screen. Can you orient it so it will be looking more planar, like rotate it, yeah, this way, square. Then let's make a screenshot of this thing, only the colorful thing. Yeah, screenshot is good. Screen clipping and select. Okay. Now and now copy paste it several times, like maybe 3 times.
Make it smaller.
Does it make sense in the a little better?
Yeah, it makes sense.
So it's like a building with several rooms,
Mm-hmm.
and we have same nature in all of them, but our main character exiting first room, coming second room, right?
Yeah.
And at the same time, there was a similar like alter ego of this character starting at the same point, but then passing through the other window, through the other door. Would you be able to explain it by your own words?
Yeah, just I guess the wave packet itself would need to continue, but if we get a
Right, right.
set
So
bound of positions.
it's called periodic boundary conditions, yes, and it is set up by defining momentum operator in such way so that when we approach the edge, the momentum will instead of using derivative between nearest neighbors, at the very edge, it will use derivative between one point on one side and another point at the very beginning. And this trick is made to avoid unnecessary errors, because if we would set a hard wall where it would bounce, it would add a lot of numerical errors. And this concept of periodic boundary conditions is especially used by polymer scientists and physicists who describe solid semiconductors and metals, because one never can simulate large enough cell to describe periodic solids, but they all repeat the same elementary units that are repeated. And if one knows all details about one elementary unit in all the other units, the process will be the same. And this concept of periodic boundary conditions allows to learn about big by modeling small. Lola, make sense? Does it make any connections to VASP calculations? Okay, Adam, are you feeling happy about this subject?
Yeah, that makes more sense to me.
Okay, yeah, thank you. We can stop sharing. Okay. Let's see where we are now. Now we have completely revisited our last week meeting and we can go forward. So the size of simulation cell versus time of simulation, right? So we are done with that. Nate, you've told that you are completely comfortable with the subject, right? Okay. Visualization, real and imaginary part of wave packet. Yes, it is basically what we did when we this illustrated discrete representation. Potential and probability distribution. Why there are three of them? Yes, oh yes, please. I have a lot of questions.
There is significance to why it's bright on this.
Yes, it's a thank you, Lola. Let me bring up the image back and rotate it a little bit. So you all are experts in electron in the free space, right? You passed through all homeworks and you know how to tell everything about this problem by pen and paper as true theorists. And when we were going over this subject in the class, we found two main features. First, center of the wave packet moves forward with linear speed, and second, the width increases quadratically. But on one hand, width increases quadratically, but the area under the probability distribution must be constant, right? So how can I do it at the same time? I don't know. I'll stop recording for a second because I'm going to pause, resume recording. So if you fill a rubber balloon with water and you like want to expand it, then how would its height change? If you pull it aside or you put it on a surface, it will be more distributed in, it will be, height will decrease. So same here. If it becomes less skinnier, it changes weight because the like area under the scarf is a constant. Does that answer your question? So absolute height gets smaller and smaller Okay, yeah. Many thanks for the question. I think we build a solid foundation for all the things, and if later we speed up for applications, we will be ready for it. So visualize potential and probability. Well, we don't have potentials yet, but let's go immediately to the subject by Joe. And after we partially cover the subjects, I will revisit this visualization. And since Mai is not on the meeting, it's better to speak directly to Joe, who is here in class. But I will come back to this number 6 and number 7. So I have two ways. One, to run another code, which is completely legitimate. I did send to all of you 3 codes. But alternatively, one can just take the code that we already have and modify it. So let's do it as a little investigation. Come on. If it will be frozen, I will need to use another computer. No, it is not. So I'm scrolling down and see where the Hamiltonian is defined. So I'm looking for the variable Ham2 and Ham3, where Ham is not food, but Hamiltonian. Okay. So Hamiltonian is momentum operator squared divided by 2 mass. And we do not have Planck constant because we agreed to work in atomic units where Planck constant is 1. And then we add square matrix with made out of V. V is potential energy. In the plane, in the free space, potential is 0. But in all situations except free space, variable V must be non-zero. So here I can do plot V. Plot V. So it is 0. If I do mesh diagonal of V, it will just convert this vector into matrix, but it is completely 0. Now let's scroll up and see where the variable V is defined. So at least where it is set up to be 0. Okay. So line 60. If I percent it out and uncomment line 59. So I can redo it writing by scratch, but it's already pre-made. So just by making this little change, I am moving from the free space to harmonic what? Oscillator, yes, yes. Because potential will be square of the coordinate. So if I want to practice this code further, I need to save it under different name. So instead of free, now it is HO. And I'll just put HO1 because maybe there were other versions of codes. Now, after this, I may want to just run the code and see what happens. So maybe it's a better way compare rather than speaking too much. So I'm running the code. It shows same initial value, but then you see it shows potential, and then potential exerts force, and then it starts oscillating force and back, right? And after the running is done, you see that observables that we were plotting before look in a different way. So the expectation value of position, instead of going on straight line, it goes forwards and backwards. Since our simulation time is limited, it makes maybe only one oscillation, but it shows different motion, right? If I practice the same commands as before, mesh S3, so we do see dramatically different picture, right? So wave packet does not approach the edge. It turns around, then changes the velocity from positive to negative, goes other direction, turns around and goes back, right? So if you want a harmonic oscillator, maybe we don't care about periodic boundary conditions. We just need them just in case. So let me quickly run over all seats and make sure you have this figure, especially Joe. Excellent. Oh, yes, yeah, very good. Yeah, if you're doing PowerPoint, still running. Press any key, so it waits until you let it go. So you can navigate to the maybe last figure, figure 11. And now it's going forward and back. Okay. Those oscillations.
What's this probability versus time?
Yes, I will explain it for sure today. Just remind me if I don't. I really want to explain it. Okay, yeah. So let's check if you have on this images online. So I'm stopping sharing. Wyatt, would you feel comfortable sharing screen?
Come back to me. I'm still getting it figured out a little bit.
Sibel, would you feel comfortable sharing screen?
Yeah, I'm trying to figure it out because I don't know. It's not.
Running? Okay.
No, it's running, but it's not giving me the same image or something. I don't know.
Adam, would you be interested?
I'm in the same boat, but I could share.
Yeah, you can share and we will debug it together.
Okay. So this is the image.
It's the old one, yes. Now HO.
But
Okay, now let's rerun this code. Yeah. So okay, click space. So it goes forward. Okay, I see what happens. The initial velocity is so high that harmonic potential doesn't save us. You can navigate to the command window and type Control C or whatever. Yeah, this is fine. You can close this window. And now let's go back to your code. Click to the code. Yes, yes, and go to the very top. So P not equals 2.25. Let's do it 0.25 or like 0.75 to have it a little more vivid. Okay, save. And run. And then we need the, yep. So the velocity is smaller. And at the very beginning, it looks a little similar to, oh no, you didn't modify the lines. You changed the name of the file, but you didn't modify the line with potential. Okay,
Didn't?
let's go to the line 59-ish, 59. Okay, so wait. The letter P in front of the letter V. And you
Oh,
know,
no.
these stupid robots, these computers, they are very non-forgiving. They look meticulous for any spelling. Okay, now let's go back to here. Aha, much better. Let's see. Slows down and turns back.
Ah.
Slows down and turns back. Okay, and yeah, so there is this little snake. So do you feel comfortable?
Yeah, that makes sense to me.
Okay, yeah, you can stop sharing.
Okay.
Wyatt, are you ready? Okay, perfect. You can stop sharing. Sibel, will you feel comfortable sharing? Sibel? Thank you.
Okay, so I'm trying to figure this out. So I guess maybe this and see, save,
Okay,
if it's gonna run the way we want it to.
okay. It looks like your wave packet still wants to go across the border.
Yeah,
So let's check what is going on. You can just erase this window.
okay.
Otherwise, you have like 21 windows.
Mhm.
So you did redefine the potential.
Yeah,
You received it as, well, maybe it's not any error with programming, but let's save it as under different name, because it's not a free wave packet. It's oh yes, thank you, Nate. Sibel,
yes.
did you hear what Nate suggests?
You just need to put a percent sign in front of the v equals x times 0. Yeah, line 60.
Oh, okay.
Yeah, thank you, Nate. So the next command discards previous value. So it was already defined. Now let's save and run.
Oops, okay. Hold on, let me just close this window. So now let me run. Uh-huh. Hold on.
Well, it's already running.
Okay.
Any key?
Well, it hasn't.
Figure.
Yeah, exactly. It's not. It hasn't opened me. Doesn't.
But maybe then no, do not push run once again.
Okay.
It's same like if you have some like a robot or a person who literally follows your commands. And oh, I'll tell a joke about my college teacher, how students were teasing him, not behind his back. So this teacher was saying a sentence or a word during a lecture, and then repeating it. Like we need to take derivative. And here's the joke. This person is coming to a food court and asking, please give me donut. Why are you giving me 3 donuts? So okay, you did resolve things. So if you if you push run 3 times, the not the hand, but the rotation symbol. Yeah, here. Yes. Okay. Yeah, I think everything is good. So if you run 3 times, it will, if you do it in a sequence, or it will try to in parallel. So if something is not working, go to the command window and type Control-C to disable previous commands.
Okay. Thank you.
Now you can stop sharing. Okay, now it's my turn to share. Application with packet code box. Oh, we need finite box. In addition, we did infinite box. Okay, we did harmonic oscillator, and we saw that position expectation value oscillates. Box and barrier, and I would say also maybe an atom, if time allows. So this last thing is top priority, and if times allows, I will return to number 6 and 7. So next designated thing is box. So in the transition period between learning and doing your projects, maybe we will do another little exercise of accompany class materials by this version of the code, because it literally shows what we are going to derive next week. So we are going to derive this motion of the wave packet forward and backward through with all our strengths. Lola did ask what is S3, right? Which we plot. So I'm quickly jumping to the main loop, and I'm navigating. First, I need to find it. So when main loop, you have a vertical line at the left. Okay, so here's loop starts, and we have a vertical line, right? Now I'm going to the end of the loop. Where all variables, all observables are computed. And here we have this S3 equals S3, and in the next line, probe 3. So it is a matrix which becomes bigger and bigger as we go through the code, and at each time it adds additional row to this matrix. So number of columns increases each time, and one row is adding, and row corresponds to new time slice, right? So we just bring it together these time slices. Oh, is it sufficient? By the way, the command mesh can be replaced by the command waterfall, and then it, for some people, it looks more visually appealing. So since we have about 700 images, they still look continuous. There is no difference. But if one looks only on a small part, it will decompose it as a independent slices. You can see it later. I just want to rush forward. So we need either a barrier or a box. And then if time allows, I will go over this variables and observables. So going back to the space before we start the loop, where we set up the potential. So basically, if you have mathematical formula or maybe an algorithm to create your potential, your function v, then you are ready to do independent project. So your creative task for doing the main part of this class, for doing independent project, is to select a natural object from chemistry, model it in form of potential, plug the potential in here, and then run it with some additional bells and whistles. And we will discuss it more, but there is an abundance, like there are almost any, with very few exceptions, problem can be projected onto one-dimensional motion and can be set up as a potential. For example, photoluminescence of metal organic dyes can be projected on one-dimensional motion for sure, even if it sounds strange. Okay, I'm looking for the line 59, where we did set up this harmonic potential, and I look if there are some pre-made writings or okay, yes, there are. So I will percent this line 59 and look here. Barrier 1. Barrier 2. Okay. Minus plus barrier 2. V equals barrier 2. So I'm uncommenting line 57, and you can and I'm saving it under save as. Instead of harmonic oscillator, I'm typing the word barrier. So if you are impatient, you can run it right away, but I'll probably quickly explain what to expect. What does this what is set up? So I'm later on I'm telling potential is equals to this function barrier 2, right? It is in the line 57. Now, and I'm commenting any other definitions of the potential V. Now, potential barrier 2 is defined as a row vector consisting of 3 segments. So the keyword once means it will be a vector filled with value of 1 as many times as many according to the value of this integer number. So we will have x2 minus ab segments here, then 2 times ab here, and x2 minus ab there. So before going forward, I may type what is this AB and what is this X2. So the total number of grid points in the simulation cell is 200. Now I chop it by 2. There is 100 there, 100 there. And then if I subtract certain small number, it will be 3 sections. A little bit less than 100 on one side, a little in the center, and a little less than 100 on the other side. Right? Is it clear? Okay. Now I'm going back to this one. So it will be just filled by 1, but then instead of 1, I multiply it by a factor. So it will be so many elements equals to minus 0.1. Then it will be so many elements equals with energy equals by 0.05. And then so many elements equals by this value. So I am doing math for a little step, right? So let's run and see and then give more comments. So I did save it as barrier. I'm running it. Going to the image. So you see, there is a one value, another value, and then lower. Right now, the initial momentum is too high, so that this problem becomes a little boring and non-interesting. So I'm going to rerun it with slightly different value. So I'll put P naught 0.25. Save. Run. Go to the image. So I did set up the kinetic energy a little smaller, and you see, instead of going through, it experiences some interaction with this barrier, right? So a little bit comes through, but most of the wave packet kind of stopped on a barrier, or it tries to be reflected. So first, how to interpret this formulation, this potential. Right now, we can stop thinking of x-axis as position of electron. It can be something more abstract reaction coordinate, but it is a universal tool to describe chemical reactions. The area on the left is energy of reactant. Area in the middle is the barrier and activation energy, and energy on the right is energy of product. So by launching wave packet from left to the right, we are starting thermally activated chemical reaction with activation barrier. Make sense? And the offset of the energy in respect to this barrier tells whether temperature is enough to overcome the activation energy, to overcome the reaction barrier. Right now, we see that there is very small probability that reaction will go forward. The yield of reaction is minimalistic. Make sense? Oh, and now we are coming to the questions that Lola whispered not very loudly, like what are these images with probability and time? Do you confirm that you asked this question? Okay, so this is yield of the reaction as function of time. Basically, it is the proportion of this part of the wave packet that passed through this barrier. And you see, since the initial energy was not high enough, the yield of the reaction will be like 15%, depending on the method we used. If I rerun this, like if I erase this things and rerun this simulation with a little higher, save. Run. Then I expect that so if yield of the reaction will be higher, so larger portion of the wave packet will pass through. See, now it goes from 15% to like more than 20. And this universal tool, if you select parameters of energy of reactant, barrier, and product, will help to predict yield of chemical reaction as function of temperature. Joe, does it make sense? Okay, so let's check where. Oh, let me inspect your sheets that you reproduce these figures, so that I'm not going too far. And we are coming about over time, but I'll try to speed up and squeeze the rest.
I just need to slow mine down.
Okay, yeah, if it goes on, everything will be fine. Okay. Okay, excellent. So it bounces back, right? And if you increase, it will reappear on the other side. Where's the command window? No, I think it waits until you push space. Oh, you did run it more than once, same as we discussed with Sibel, like donut, donut, donut.
So am I supposed to go? Going really slowly, so there's something I need to change. What did I change?
No, everything is good.
Why did my own look funny? It's really slow.
But it is okay. I do not see any big problems. So
So how do you increase the motion because it's like very slow?
so if we keep increasing kinetic energy, temperature, and momentum, it larger portion will get through. But then this portion will bounce the edge, and it will be not realistic anymore. So then we will need to expand the size. So right now, for the proof of concept, we are fine. And later, if you select it as a research, one can do more things. So let me quickly. If anyone needs to depart immediately? Are there anything? Any reasons to?
Prefer to, but like how much longer?
Maybe let's do a step, just one more potential, and then depart. So stop sharing. Wyatt, would you share screen?
I don't have it on. I missed exactly what you did in a step, and so I
We can debug
didn't
it
get
together. Just share and we'll debug it. It's a matter of 15 seconds. So let's go to the line 57, 59, 57 in the stop. So comment out line 59%, then uncomment line 57, remove %, save as and a different name, tell something about barrier at the end. Okay, save. and run. You can just run by green triangle, yes. Space, click space. So now you see it passes through your barrier. Later on, you can rerun it with smaller value of initial momentum. But I think you've got the idea, right? Okay, thank you. Sibel,
Yes, thank you.
thank you. Sibel, would you share a screen? Okay, yes, I see you did run it successfully, and you put enough energy to overcome the barrier, but then size of simulation cell was too large, so it gets to some numerical issues which we will debug if you do it for productive research. Everything is excellent. You can stop sharing. Adam, would you like to share screen? Perfect, perfect. I'm happy. Please stop sharing. Share screen. Share. Close, close, close. And now I need to do, instead of barrier, I want a box. So we used some time to study particle in the box. So I need the line. Okay. And where do I define values A, B? I can use it a little bigger. So instead of 7, let me put it like 20. And to do it in a quickest way, I will just put the sign minus in front of it. So I put and then save it, save as box. Box and run. So you see, now we have a box, and with packet, if energy is high enough, it will try to escape it. But basically, since energy is negative, substantial part of the probability is trapped inside this box. So this models the chemically stable systems, like electron trapped in the conjugated polymer or a molecule or a semiconductor. So please try to do this exercise, and let me bring up the. So we are done finite box, barrier, and harmonic oscillator items for future. You know how to do movies, and we did visualize observables. When the code is done, the main variables are plotted here: expectation value of position, uncertainty, and this probability distribution, which we just chop this probability distribution on two things and integrate from center to the left and from left to the center and from center to the right. And it will be probability of reactant and probability of product, which are plotted here. So at initial time, the probability of reactant is 100%, probability of product is 0. As the reaction goes through, they may exchange. I think we are over time. So everyone, let's announce that formal part is done. Everyone is welcome to depart or disconnect, but I'll stay here and answer any questions and do more demonstrations if needed. But if you probably have some scheduled appointments, so do not worry. Main part is already delivered. Joe, do you have any questions, or it is enough for your presentation? Okay. Joshua, do you have enough for your presentation? Well, would you do just a little bit as an independent glance? Your vision of the things can be different, and it will be complementary. So just a couple of minutes. Yeah, thank you. Just a second, I'll check if, why do you have any emergent questions about this materials?
No, I'll be sure to watch the recording from the previous and then let you know if I have any questions after that.
Okay, okay. Yep. I do have recordings of the presentations like you are going to do on Friday from previous years. They're on my YouTube channel, and I can share links if you're interested. But as soon as you have all ideas, it could be just waste of time. But if anyone is interested, I do not mind sharing. Okay, so Sibel, do you have any questions, or you feel comfortable?
I'm good.
Okay.
I'll just watch the recording and yeah.
Yeah, thank you, thank you. I plan to send today's recording by about midnight. Adam, do you have any questions or concerns? How comfortable you are?
Yeah, I'm much more comfortable now.
Okay.
Thank you.
Yeah, thank you. I'm looking forward to see your PowerPoint next night.
Yeah, I'll see you then.
Okay. Okay. Yeah. Have a good night.